Imagine a world where machines understand our languages. This is not a scene from a science fiction movie, but the fascinating realm of computer science. In this world, we use mathematical models called automata to represent abstract computing devices. These devices can accept or reject strings of symbols based on a set of rules. Among these models, finite automata are the simplest yet powerful tools for recognizing patterns within strings. They are the fundamental building blocks of more complex computational models and find applications in various fields, including compiler design, text processing, and artificial intelligence. Think of a vending machine as a basic example of a finite automaton. It accepts coins as input and dispenses a product only when a specific combination of coins is inserted. This simple machine embodies the essence of automata, a system with states, transitions, and an ability to recognize specific patterns. Our journey into the world of automata begins with understanding two fundamental types: Deterministic Finite Automata, or DFA, and Nondeterministic Finite Automata, or NFA. These models, while conceptually different, share a common goal: to recognize regular languages, a class of formal languages with immense practical significance. Let's begin our exploration with the Deterministic Finite Automaton, or DFA. A DFA is like a well-organized traveler who plans their journey meticulously, knowing every step in advance. It operates on a set of states, and at any given moment, it can only be in one state. Think of these states as cities on a map. The DFA starts its journey from a designated start state and reads symbols from an input string, like following directions on a map. Each symbol guides the DFA from one state to another, following predetermined transitions. If the DFA reaches an accept state, also known as a final state, after reading the entire input string, it means the string is accepted. This acceptance signifies that the string belongs to the language recognized by the DFA. On the other hand, if the DFA ends up in a non-accept state or encounters an undefined transition, the string is rejected. Consider a DFA designed to recognize binary strings ending in 0-1. It would have a specific set of states with transitions defined for input symbols 0 and 1. Only upon reaching a state after reading 0-1 at the end of the input string would the DFA accept the string. DFAs, with their predictable nature, provide a clear and unambiguous way to define patterns within strings. They form the foundation for understanding more complex automata and are crucial in various computational tasks. In contrast to the meticulous DFA, the Nondeterministic Finite Automata, or NFA, is more of an adventurous traveler, open to exploring multiple paths simultaneously. This flexibility arises from the NFA's ability to be in multiple states at the same time. Imagine our traveler standing at a crossroads, unsure of which path to take. An NFA, in this situation, would replicate itself with each copy exploring a different path. This ability to be in multiple states simultaneously allows the NFA to explore all possible paths through the state diagram concurrently. NFAs also introduce the concept of epsilon transitions, which are transitions that occur without consuming any input symbol. It's like our traveler teleporting from one city to another without following any road. These epsilon transitions add another layer of flexibility to the NFA's journey. The acceptance criteria for NFAs are also different from DFAs. An NFA accepts a string if at least one of its parallel explorations leads to an accept state after reading the entire input string. It's like our traveler finding at least one path that leads to the destination. While NFAs might seem more complex than DFAs, their flexibility makes them powerful tools in certain scenarios. They are often easier to design for recognizing specific patterns and can be particularly useful in proving the properties of regular languages. Despite their contrasting approaches, DFAs and NFAs are surprisingly equivalent in their power to recognize languages. This equivalence forms a fundamental concept in automata theory, stating that any language recognized by an NFA can also be recognized by a DFA and vice versa. This equivalence might seem counterintuitive at first. How can a machine that follows a single path be as powerful as one that explores multiple paths simultaneously? The answer lies in the fact that while an NFA can be in multiple states, it doesn't mean it can do more than a DFA. Think of it this way. The NFA is simply exploring all possibilities in parallel, but it's still limited by the same set of rules and transitions. It's like searching for a key in a maze. Exploring multiple paths simultaneously might seem faster, but ultimately there's only one path that leads to the key. The equivalence of DFA and NFA has profound implications. It allows us to choose the model that best suits our needs for a particular problem. If we prefer a simpler implementation, we can opt for a DFA. If we need a more intuitive representation for a complex pattern, we can choose an NFA, knowing that we can always convert it to an equivalent DFA if needed. Section 5. The power of transformation, from NFA to DFA. The equivalence of DFAs and NFAs is not just a theoretical concept, it comes with a practical method for transforming one into the other. Specifically, we can convert any NFA into an equivalent DFA using a procedure known as the subset construction algorithm. This algorithm systematically creates states in the DFA corresponding to sets of states that the NFA could be in simultaneously. Each state in the DFA represents a snapshot of all the possible states the NFA could reach after reading a particular sequence of input symbols. The transitions in the DFA are then defined based on the transitions of the NFA. If a symbol can lead the NFA from a state in one set to a state in another set, then the DFA will have a corresponding transition between those two sets. While the subset construction algorithm guarantees the creation of an equivalent DFA, the resulting DFA might have more states than the original NFA. This increase in states is the price we pay for converting non-determinism into determinism. The ability to convert between NFAs and DFAs is a testament to the robust nature of regular languages and provides us with flexibility in choosing the most suitable model for designing and analyzing computational systems. Section 6. Regular Grammars, RG. The blueprint of language. Having explored the world of automata, let's shift our focus to another fundamental concept in formal language theory: regular grammars, RG. Grammars in general provide a formal way to describe the structure and syntax of languages. They are like blueprints that define the rules for constructing valid sentences in a language. Regular grammars, specifically, are used to describe regular languages, the same class of languages recognized by DFAs and NFAs. These grammars use a set of production rules to generate strings belonging to the language. Each production rule in a regular grammar consists of a non-terminal symbol, which acts as a placeholder for other symbols, and a replacement sequence, which can be either a terminal symbol, a non-terminal symbol followed by a terminal symbol, or simply an empty string. These production rules act as instructions for building strings. Starting with a designated start symbol, we apply these rules repeatedly, replacing non-terminal symbols with their corresponding replacements until we obtain a string consisting solely of terminal symbols. Regular grammars provide a generative approach to defining languages. Instead of defining what strings are accepted, as we do with automata, we define how to generate valid strings from scratch. Section 7. Right linear and left linear grammars, two sides of the same coin. Within the realm of regular grammars, we encounter two specific forms: right linear grammars and left linear grammars. These forms differ in the way they structure their production rules, yet they both possess the same expressive power, meaning they can generate the same class of languages. Right linear grammars, as the name suggests, have production rules where the non-terminal symbol is always on the right side of the replacement sequence. This structure ensures that the generation process proceeds from left to right, adding terminal symbols to the right end of the string. On the other hand, left linear grammars have production rules where the non-terminal symbol is always on the left side of the replacement sequence. This arrangement leads to a generation process that proceeds from right to left, adding terminal symbols to the left end of the string. The distinction between right linear and left linear grammars is primarily a matter of perspective. Both forms are equally capable of describing regular languages, and the choice of which form to use depends on the specific application or personal preference. Understanding these different forms of regular grammars provides us with a more comprehensive toolkit for analyzing and manipulating regular languages. Section 8. From grammar to automata building bridges. The connection between regular grammars and finite automata runs deep. Not only do they both describe regular languages, but we can also systematically convert between them. This conversion process highlights the inherent relationship between these two seemingly different formalisms. Converting a regular grammar to a finite automaton involves creating states in the automaton corresponding to the non-terminal symbols in the grammar. The transitions between these states are then defined based on the production rules. For each production rule, we create a transition in the automaton from the state representing the non-terminal symbol on the left side of the rule to the state representing the non-terminal symbol on the right side, if any, labeling the transition with the terminal symbol present in the rule. Except states in the automaton are determined by the production rules that generate terminal symbols directly from the start symbol of the grammar. This process ensures that the resulting automaton accepts the same language generated by the original grammar. The ability to convert regular grammars to finite automata allows us to leverage the strengths of both formalisms. We can use the intuitive nature of grammars to define the structure of a language and then convert it to an automaton for efficient recognition or manipulation. Section 9. From automata to grammar reverse engineering language. The bridge between regular grammars and finite automata is a two-way street. Just as we can convert a grammar to an automaton, we can also reverse the process and convert a finite automaton to an equivalent regular grammar. This reverse engineering process involves creating non-terminal symbols in the grammar corresponding to the states in the automaton. The production rules are then defined based on the transitions between these states. For each transition in the automaton, we create a production rule in the grammar. The left side of the rule consists of the non-terminal symbol, representing the origin state of the transition, while the right side consists of the terminal symbol, labeling the transition, followed by the non-terminal symbol representing the destination state. The start symbol of the grammar is the non-terminal symbol representing the start state of the automaton. The production rules that generate terminal symbols directly from the start symbol correspond to the accept states in the automaton. This conversion process demonstrates the tight coupling between regular grammars and finite automata, showcasing their ability to represent the same underlying information in different but equivalent ways. Section 10. The grand unification equivalence of regular grammars and DFAs. The ability to convert between regular grammars, DFAs, and NFAs reveals a profound truth in the theory of computation. These three formalisms are simply different facets of the same underlying concept: regular languages. This equivalence has far-reaching implications. It tells us that we can choose the most suitable tool for the task at hand, knowing that we can always switch between them without losing any information or expressive power. If we find it easier to define a language using a set of generation rules, we can opt for a regular grammar. If we need to implement an efficient algorithm for recognizing strings belonging to the language, we can choose a DFA. And if we want to leverage the flexibility of non-determinism for certain tasks, we can utilize an NFA. The equivalence of regular grammars, DFAs, and NFAs underscores the elegance and robustness of the theory of computation, providing us with a powerful toolkit for understanding and manipulating formal languages. Section 11. The significance of regular languages, a foundation for computation. The study of regular languages, encompassing regular grammars, DFAs, and NFAs, is not merely an academic pursuit. It forms the bedrock for numerous practical applications in computer science and beyond. Regular expressions, a powerful tool for pattern matching and text manipulation, are directly based on the principles of regular languages. Lexical analysis, a crucial phase in compiler design, relies heavily on finite automata to recognize and categorize tokens in source code. Furthermore, regular languages find applications in diverse fields such as natural language processing, communication protocols, and circuit design. Their ability to represent simple patterns efficiently makes them invaluable tools in various computational tasks. The study of regular languages provides a fundamental understanding of computation, laying the groundwork for exploring more complex formal languages and computational models. It is a testament to the power of abstract thinking in solving real-world problems, and continues to shape the landscape of computer science today.